Let's talk about thermochemistry's revision. So in thermochemistry, you need to understand the terms like what is exothermic, which means delta H of the reaction is less than 0. Then endothermic, which means delta H of the reaction is greater than 0. Then exergonic, which means delta G of the reaction is less than 0. Then we have endergonic or endogonic, delta G of the reaction is greater than 0. First, remember these two terms, beta. Clear? Next.
Yes.
Second term that you need to remember is that delta H of the reaction is always equal to enthalpy of the products minus enthalpy of the reactants. Got it? For any chemical reaction, you will be able to write this down. Okay. Next, delta H in general for a non-reacting gas will be equal to QP, delta H of the reaction. Delta H of the reaction, sorry, for a reacting gas will be equal to QP. That means heat released at constant pressure. Delta U of the reaction will be equal to QV, heat released at constant volume. Heat released or required, anything, okay? You know that H is equal to, next one, H is equal to U plus PV, which you are aware of, which I can write it as delta H is equal to delta U plus delta of PV. Barabar? And for an ideal gas, this one, for an ideal gas, any change in the PV can be associated at delta NGRT at constant
Yes.
temperature. And usually reactions, chemical reactions are operated at constant temperature. Hence, delta H of the reaction can be written as delta U of the reaction plus delta NGRT. And you know that delta Ng is summation of number of moles of the products minus summation of number of moles of the reactant. Got it? So this is one thing you must know. You know how to use this term basically. Okay, इस term को use करना आना चाहिए. The
Yes.
next important term is about enthalpy of formation. Enthalpy of formation. Enthalpy of formation is delta H naught of F. This is how we write it down. Okay. So basically, whatever delta H of formation is, we are trying to figure out formation from any formation from elemental forms, elemental forms of all elements present in the molecule, all elements present in the compound, present in the compound. From everything should come from the elemental form of it. Clear? And at a reference temperature. So we can take reference temperature if nothing is given. You can take it as 25 degrees Celsius as 298 kelvins. Okay. And so for delta H of formation, delta H of formation at 1 atm and temperature 298 kelvins is generally taken as 0 for pure and elemental forms. Elemental forms. Got it? This is the next understanding we should have. For example, delta H of formation is 0 for which of the cases here? Carbon as a part of graphite solid. Its delta H of formation is 0. Got it? Next, bromine in its liquid state. Next, iodine in its solid state. Next, H2 in its gaseous state, oxygen in its gaseous state, fluorine in its gaseous state, chlorine in its gaseous state. nitrogen in its gaseous state, okay, sulfur in its orthorhombic rhombic allotropic form, then P4 in its white allotropic form, P4 in its white allotropic form. Next, H plus in aqueous solution also is 0. H plus in aqueous solution is also in, and thin gray solid is 0. These are the ones you should definitely remember. Okay. Is this part clear, beta? Next thing.
Yes.
A general reaction like 2A plus B is giving, let's say, 3 plus C plus 3D. Then delta H naught of the reaction can always be written as delta H naught formation of C plus delta H naught formation of D into 3 times that minus A times of delta H naught formation of A. Okay, H naught formation of A plus uh, delta H naught formation of B. Okay, this is what we are supposed to get. Clear?
Yes, sir.
Next. The next term what you need to remember from here is enthalpy of combustion. Enthalpy of combustion. Normally we write this as delta H naught of combustion. This is how we write it down. Okay. So basically here it is heat released. Okay, heat released when any compound is burned in excess amount of oxygen, excess or sufficient amount of oxygen, okay, to form, okay, uh, carbon dioxide, that means it will get complete oxidized, and water H2. So delta H of combustion is equal to minus 890 kilojoules per mole. So this is the form which you will have. Got it? So this is the amount of energy which is released. Clear with this part? Enthalpy of combustion it is. Okay. So usually enthalpy of combustion, if it is given, there are two terms we should understand here. One is, what is bomb calorimeter? Bomb calorimeter. Bomb calorimeter is a term used when the volume change is zero in the reaction. So that means whatever the heat that is released is at constant volume, and that will only change the enthalpy of the it will only change the internal energy. Second one is cup calorimeter. In that case, delta P equal to 0. So in that case, QP is equal to delta H of the reaction. Okay, QP is equal to delta H of the reaction. Got it. Now, when we write this one, QV is equal to delta U of the reaction, which is bomb calorimeter. Now, uh, whenever you are writing the equation, make sure that whatever the energy, whatever the heat that is being given, it is always converted into internal energy. And
Yeah.
using this only, we can calculate, putting this into the formula, that is delta H is equal to delta U plus delta NGRT. ये use करना चाहिए बस questions में. Okay, बेटा? Right. So this is what you need to know it from combustion. Second thing is from enthalpy of solution. Enthalpy of solution, which is delta H naught of solution. Hmm? So it is the heat released or absorbed when 1 mole is dissolved in excess amount of solvent, excess amount of water. So for example, MgSO4 solid is there and I'm adding in water which is excess. Got it? So then this will convert into Mg2 plus aqueous plus SO4 2 minus aqueous. correct? So delta H naught of the solution, which is given as minus 91.2 kilojoules per mole. What does this represent? ये positive भी हो सकता है, negative भी हो सकता है. It is not something which in our hands. Okay. But this infinite amount of water, if you're using, then the energy released or absorbed is called delta H of the solution. Okay, beta.
Yeah.
And delta H of the solution for a crystalline salt. This is a crystalline salt, right? For a crystalline salt, we can always write it as delta H of the lattice energy plus delta H of the hydration energy. This is what it should be. Correct? And this could be again positive or negative. Got it? So if delta H naught of lattice is greater than 0, okay, I mean, sorry, if this is greater than delta H naught of hydration. So we notice this part here that this is always positive, this is always negative. Okay. So in that case, if delta H naught of lattice is greater than this one, so it is an insoluble form or sparingly soluble salt. Next, delta H naught of this is less than delta H naught of hydration. Okay, then it is
Hmm.
soluble salt. Then this is soluble salt, and delta H naught of lattice is equal to delta H naught of hydration. Then it is saturated salt, saturated solution, saturated salt solution. Okay,
Yeah.
so these are the forms we must know. And next one is enthalpy of hydration. Enthalpy of hydration. Hydration actually है ना बहुत सारे terms है. Hydration can be used in multiple ways. We can use hydration even in this one also. When energy is released or absorbed, when an anhydrous or partially hydrated salt is been added to water for crystallization. That is
हाँ.
CuSO4 solid plus 5H2O liquid. अब ये solid ही बन रहा है वापस CuSO4 dot and 5H2O solid. Correct? So
Hmm.
in that case, the energy which is released will be called as, in fact, this is what is coming out, and we call in such cases as hydration energy. Okay, कि
हाँ.
पूरा नहीं हो रहा है, सिर्फ इतना ही रिलीज हो रहा है. ठीक है बेटा. So
Yes.
this is called delta H of hydration as well. Now, what is lattice energy? Lattice energy मैंने ऊपर लिखा है already. Lattice energy can be written as LE or delta H of U. So lattice energy is basically if you have any salt like Mn salt here, correct? If you have it in gaseous state, M plus and N minus gaseous state, then delta H of the reaction, this is lattice, which is energy required. If you put the same thing reverse, then that is also lattice, but lattice released.
Hmm.
Next one is hydration energy of ions, hydration of ions. Earlier ऊपर जो देखा वो था hydration of salts. This is about hydration of ions. So that is if you have M plus and if it is converting into M minus, sorry, M plus aqueous or
Hmm.
N plus N minus converting into N minus aqueous, then the energy released is called as hydration energy, right? This is for the cation, and here will be energy released as well. And hydration energy in this case is for anion. Here also energy is released. So this is hydration energy. Beta.
Yeah.
Okay. Next. Next one is enthalpy of neutralization.
Yeah. Hmm.
Okay, let's see what is enthalpy of neutralization. Suppose if you have H plus and OH minus, both of them are reacted by one equivalent each. This is one equivalent to form 1 mole of H2O. Correct. Then the energy released in this case is called as neutralization. And the value of that is minus 57.3 kilojoules per mole. Or it is minus 13.7 kilocalories per mole. Got it?
Hmm.
This is called delta H of neutralization. And you can notice that for a strong acid and a strong base, the value will remain the same beta. Got it?
Yeah.
But if you have a weak acid plus strong base of one equivalent each, ये दोनों को react किया मैंने. So then I will get this as, weak acid will convert into something like A minus. Sorry, I'll do one thing. I'll write it as HA. Weak acid is HA, A minus plus H2. So this is kind of getting neutralized as well. But in this case, this is delta H of neutralization dash. So that is, magnitude wise less than 57.3.
Yeah.
57.3, which is kilojoules per mole. Correct?
Yes.
Now, what is the differential amount of energy? The difference energy is called the dissociation energy. So the dissociation energy is equal to delta H of neutralization dash, which means this is for weak acid and strong base, plus delta H naught of neutralization, which is for strong acid and strong base. Got it?
Hmm.
And this value delta H of dissociation will be greater than zero overall. Overall, dissociation is always required energy. Okay,
Yeah.
beta. So in case if you come across this question, you should be able to figure out what is this delta H of dissociation. Second thing, how do we calculate the alpha? Alpha can be calculated as 1 minus delta H of dissociation, 1 minus delta H of dissociation, which is, practically observed how much it is, divided by delta H of dissociation, which is theoretically calculated. So here it is mostly calculated part. So this entire thing into 100. So that will be your alpha value, which is degree of dissociation. So it is degree of dissociation. So you should know this formula, how to use that. Okay.
Uh,
Dissociation is the one which is, sorry, practical one is the one which you need to calculate. Dissociation 100% 100% रिएक्टेंट के लिए कितना होना चाहिए ये आपको क्वेश्चन में दे देगा. Usually in question the denominator is given, you need to find out the numerator value. Okay, so that is your degree of dissociation. Hmm? Next one is heat of dissociation. Okay, heat of dissociation is delta H naught of bond, you can write it like this, sorry, delta H naught like this, bond dissociation. Okay, or usually we write it like this, enthalpy of some bond here. Correct, this is the other way of writing. So what does that mean? Suppose if you have H and H, which is in gaseous state, and you're converting that into 2H gas,
hmm.
and the delta H naught of bond dissociation energy is given as 103 kilocalories per mole. ये ऐसे दिया है समझो. Then I can write epsilon of H and H is equal to 103. Got it?
Yeah.
So this is a way to represent epsilon. Next one is enthalpy of atomization.
हाँ.
Right. Enthalpy of atomization is basically you are converting any kind of a form into atomic form. Like sodium solid is there.
Yes.
You sublimate into gaseous. So that means it is atomization. So in this case, this is the atomization of sodium salt, which is also the sublimation of sodium salt. Clear?
Yeah. Yes.
And similarly, you can have something as simple as H and H of gas is giving 2H gas. Even this is also atomization of H2, which is nothing but epsilon of H and H, correct?
Yeah.
Suppose if you have CH4 gas to C and 4H, this is also delta H of A, between C and H bond to be broken. Sorry. Atomization is equal to, it is all about breaking all four bonds. So we can say we can average it out 4 into epsilon of C and H. So atomization is converting everything into atomic form. Hmm?
हाँ.
Any doubt?
No, sir. Understood.
Right. Next. Last enthalpy form is about enthalpy of phase transition.
Yeah.
Enthalpy of phase transitions.
Yeah.
For example, solid to liquid, we call it as fusion. Okay. Then
Yeah.
liquid to gas, we call it as vaporization. Enthalpy of vaporization.
Yes.
And solid to gas. Solid to gas. It is called sublimation. Hmm? Next.
Yeah.
Liquid to solid. Liquid to solid is called freezing.
Yes.
And gas to liquid is called condensation.
हाँ.
And gas to solid, right? So this is condensation. Gas to solid is called deposition. Any doubt? In
No,
this
sir.
case,
Understood.
please check.
No,
Understood,
sir.
right?
Understood. Yes.
Generally, what you will notice is that delta H of sublimation is always equal to delta H of fusion plus delta H of vaporization for a substance. Okay.
Yeah.
Next, all is all about application beta. Okay. The
Yeah.
first applications. What is applications? The first application is Born-Haber cycle.
Yes.
Born-Haber cycle is used to calculate lattice energy.
हाँ.
Unknown lattice energy. For example, if you have the overall reaction like this, NS solid plus half Cl2 gas, that is giving NaCl solid. Okay.
Yeah.
And delta H of formation. Got it? See, Na solid is giving
हाँ.
Na
Delta.
gas. So this is delta H of sublimation.
Yes.
Okay. And half of Cl2 gas is becoming Cl gas. Got it?
Yeah.
So that is half of bond dissociation of Cl and Cl. Then sodium gas is getting ionized, Na plus gas. So that is delta H of ionization energy. Next, chlorine which is formed as a gas is getting Cl minus gas, which is Cl minus gas, which is uh, electron gain enthalpy. This is electron gain enthalpy. Now, once you get this, you have Na plus gas plus Cl minus gas. Both are becoming 1 mole of NaCl. Then the energy released in this case is what we call it as lattice energy. This is lattice energy. So
Yeah.
therefore, delta H of formation of NaCl. Finished? Hmm.
Yes,
See,
sir.
delta H of formation of NaCl will be equal to sum of all these energies. Delta H of sublimation plus half of epsilon Cl and Cl plus delta H of ionization plus delta H of electron gain enthalpy प्लस डेल्टा एच ऑफ लैटिस. बस ये सबको ऐड करोगे तो यहां से अननोन लैटिस एनर्जी कैन बी फाउंड बिकॉज रेस्ट ऑल विल बी नोन फैक्टर्स.
Yeah.
राइट, सो दिस इज अ स्टैंडर्ड एग्जांपल दैट यू नीड टू अंडरस्टैंड. ओके बेटा.
Yes.
नेक्स्ट, second application is about using bond enthalpies to find delta H of formation. For example, let me write this one. Let's say CH4 gas is been treated with half uh, CH4 gas is treated with 2O2 gas that is giving CO2 gas plus 2 moles of H2O liquid, correct? Now,
Yes.
ये एक अच्छा एग्जाम्पल है समझने के लिए. This is delta H naught of combustion of methane, correct? This is the combustion of methane. Okay. Now you notice this, the combustion reaction can be written in so many different forms. That is delta H of combustion of this reaction can be written as enthalpies of formation of the products. So enthalpy formation of carbon dioxide plus 2 times of enthalpy formation of water in liquid state minus enthalpy of formation of methane minus 2 times of enthalpy of formation of O2. Now we just learned that enthalpy of formation of water O2 is zero,
Yeah.
correct? Because it is coming from a elemental form. So elemental form delta H of formation is zero. So if I put that, this is the value I'll get. So delta H of formation of carbon dioxide. If these are known values given, then whichever unknown is you can find out. Done?
Yeah.
But if you have to write the same delta H of combustion in terms of bond energies, then I will write it as enthalpy of bond energies of the reactants minus summation of bond energies of the products.
Yeah.
So that's the main difference. For enthalpies, you will write it as products minus reactants. For bond dissociations, we write it as reactants minus products. Okay.
Yeah.
And see on the reactant side, what do we have? I have CH4 as a gas. And
Yeah.
CH4 is 4 bonds of epsilon CH plus 2 times of epsilon of O double bond O. ये हो गया reactant side के enthalpies minus product side. Product side में क्या है बेटा? So on the product side, it is C double bond O. Correct. So इसका मतलब है we have 2 times of epsilon C double bond O. Okay. That
Yeah.
plus H2O. 2 times of epsilon O and H का bond तोड़ना है. बराबर.
Yes.
But this is not correct because enthalpies can also only return, sorry, bond dissociation can only be written when they are in gaseous state. क्या ये gaseous state में है? 9. So which means I will also have to add one more factor into it. Okay? To convert that into gas, I will have to add 2 times of delta H of, this is from liquid to gas. Liquid to gas is vaporization. Delta H naught of vaporization of H2O liquid. Clear
Yes.
now? This is what
Yeah.
you should be able to write. So basically for any equation, either this or this should be used in the form, in the terms of formation or in the
Yeah.
terms of bond dissociation. Okay?
Yeah.
So if you use it, anything which is unknown can be figured it out from these cases.
Yes, sir.
Correct. Next. Third application is resonance energy.
Yeah.
Resonance energy. So whenever there is a difference in the delta H of the reaction, I can say resonance energy is equal to delta H of formation, which is actual amount, minus delta H of formation, which is calculated amount. Okay. For actual
Yeah.
amount, resonance energy would be always lesser than that of resonance energy of the calculated form. So you will see usually delta H of formation of actual is always less than delta H of formation of calculated. Okay,
Yeah.
which implies resonance energy is always less than zero. Hmm.
Yeah.
It's a released energy always. Okay,
Yes.
next. Now, the same thing if at all I write in terms of the other factors. For example, benzene का example ले लेते हैं. Okay,
Huh.
so benzene, if you have cyclohexane plus H2 and it is converting into cyclohexane, then the energy is released in this case. And this energy released is called hydrogenation. Here HYD represent hydrogenation.
Yeah. Okay.
So hydrogenation is the amount of energy released when you are adding a hydrogen to molecule. Okay, this is hydrogenation. Clear?
Yeah.
Next. If you have to write the benzene form, correct, plus H2, and then theoretically we are trying to get this here 3 moles, correct? So
Yes.
calculated delta H of the hydrogenation, which is calculated, that is how much this can give. Delta H, sorry.
Mm.
See, if it comes to calculated amount, how do we check it out? So we expect that we are adding 3 times of that of delta H of hydration of, cyclohexane, correct? Delta H of hydration of cyclohexane. Because अगर ये 1 mole के लिए, I mean for 1 pi bond this much amount of energy is released. For 3 pi bonds, how much amount of energy will be released? Theoretically, this much is supposed to be released. Okay,
Yes.
but practically, resonance energy will be equal to this much amount of energy is released, right? So that is delta H naught of hydration, which is calculated, minus delta H naught of hydration, which is actual, correct? Can you see the
Yes.
difference now? This is when you write in terms of formation, it is actual minus calculated. When you write in terms of hydrogenation, it is calculated minus actual. Okay. Same
Yeah.
way, resonance energy can also be written as delta H naught of combustion calculated minus delta H naught of hydration, delta H naught of hydration. Right. So this is about calculated minus actual. So please check. Did you understand what is the resonance energy? How to be write depending upon whatever the factors that is given. Okay, beta.
Mm.
Next. The fourth application is about Kirchhoff's law. Kirchhoff's law. Kirchhoff's law is basically enthalpy calculation at two different temperatures. Delta H2 minus delta H1 is equal to delta of NCP multiplied by delta T. ये होता है. Okay.
Yes.
And delta of NCP of the reaction is equal to, okay, summation of NCP of the products minus summation of, next, this is N times of CP of the reactant.
Yeah.
So this is Kirchhoff's law. और simple terms में बताऊं तो ऐसे delta H2 is equal to delta H1 at temperature T. Sorry, delta H at temperature T is equal to delta H naught of temperature naught plus, and this will also give when it comes to delta H naught here. So that means uh, what is left in that case? This is a temperature T. So we will have this as delta NGP into T, because T2 minus T1 में से T निकाल दो. Correct?
Yes.
So this delta CP of the reaction
Yeah.
into T. This is what we should have it as delta H of T. Are you clear with that?
Yes. Yes, sir.
Okay. Now, last thing is finding out delta G naught of the reaction. Same thing, delta G naught of the reaction can be written as delta G naught of the products minus delta G naught of the reactants.
Yeah.
Right? And this delta H of products can also be written as delta H naught of products minus T delta H naught of products.
Hmm.
Delta H naught of products. This entire thing minus, right, this is of reactants minus T delta S naught of the reactants.
Yeah.
That, that's it. Yeah, theoretically, this is how much you need to know from this topic. Correct? So
Yeah.
what is thermochemistry? Correct? What are the terms that you need to know for solving the questions? Clear, beta?
Huh.